Before we begin, I'd just like you to have a look at the periodic table of elements again, and you may notice that there's kind of a box down the bottom with two groups in them called the lanthanides and the actinides. Now the reason they're kind of sometimes separate, and if you look at your logbooks, if you go to page 79 of your logbooks, that's your periodic table, and it refers you to page 82 for the lanthanides and actinides. That's basically because in addition to being grouped in order of increasing atomic number, the periodic table is also grouped based on how the different elements react by their reactivity, mainly down to their electron configuration. And the lanthanides and actinides are kind of separate. So just, especially when we come on to the next unit on fusion and fission, a lot of the elements we're dealing with will be in there, so just know where to find them as well. Last time we said that there were three types of ionizing nuclear radiation: alpha, beta, and gamma. So before we talk about how we can detect this ionizing radiation, we need to just briefly go over what an ion is. And in essence, an ion is just a charged particle, a particle that's either gained a positive or a negative charge by the gain or loss of electrons. So let's look at an example of a negative ion. So here's an atom of fluorine. It's got 9 protons in its nucleus. We're not too fussed about neutrons at the moment, so just keep focusing on the protons. It's 9 protons, there's its 9 electrons scattered around nearby, and you'll get 2 in the first shell and 7 in the second. Now, I don't want to anthropomorphize them, I don't want to make them think that they want things, but they prefer to have a full outer ring. So they prefer to have 8 electrons in the outer ring. And if they can get that electron from somewhere, it'll make them much more stable. So if they're able to get that extra electron, they'll accommodate it in the outer ring to get a full outer ring. But now, they still have 9 protons in their nucleus, that's not changed, but they've now gained an extra electrons, they've got 10 electrons. So the overall balance there is you've got 9 positives and 10 negatives. You've got an overall charge of -1, so it's become an ion. Specifically, this is a type of an ion, the negative ones. And as an example of a positive ion, here is an atom of lithium. So it's got 3 protons in its nucleus and 3 electrons. And in terms of getting a full outer shell, it's much harder to gain 7 extra electrons from somewhere than it is to simply lose 1. Now, I'm oversimplifying here, it's a bit more, there's more to it than that, but lithium will lose its electron quite readily. So if it does, it's still going to have 3 protons in its nucleus, but now it's only going to have 2 electrons in its first shell, and that means that you've got an overall net charge of +1, so it's a positively charged ion referred to as a cation. Now that we've reminded ourselves what an ion is and how it's basically a charged particle, so it's got electrical charge, we can use the electroscope to detect ionizing radiation. So if you put a bit of charge on the leaves and then bring a radioactive source near to the plate, the charge will start to dissipate and the leaf will start to go down. Or if you bring a like charge to it, the leaf will bend out more. So you can see by its deflection that the radiation is ionizing. While the electroscope can help us to detect the presence of ionizing radiation, it doesn't really help us to quantify how much, and there's a big difference in terms of how much radiation you're actually getting. The amount really does matter, so we need to get an idea about that. So to do that, we're going to need, there's one of 2 options. The one we're going to look at first is the Geiger-Müller tube. Now before we really tackle that, I just want to go into a bit more detail and clarify what happens when radiation ionizes something. We're going to use argon as an example because it's a component of the Geiger-Müller tube. So here we have an atom of argon. Now some tubes use neon, some use helium, but they're all noble gases and they're all stable. So they've all got a full outer ring, that's the key here. So let's start off with our argon. It has a mass of 39.95. That's because most of its isotopes have 22 neutrons. It's got its 18 protons there in the nucleus. So here's the electrons. You've got 2 in the first string, 8 in the second, and 8 in the third. Okay, but here comes some ionizing radiation. We've got alpha, we've got beta, we've got gamma. Today, for this example, I've chosen alpha, and it could have used any of these, it doesn't matter. But the alpha radiation comes along. What it does is it knocks off an electron out of the outer shell of the argon atom. What that means is that electron then kind of goes flying off on its way. The alpha particle also goes flying off on its way. But the argon atom is left with a net positive charge because it's lost an electron. And that electron is itself an ion because it's a charged particle. So you've now separated the argon neutral atom into a positively charged ion and a negative charged one. Okay, we're getting a lot closer to understanding how the Geiger-Müller tube works. And just before we move on, let's kind of simplify what we looked at before. And I'm going to refer to these argon atoms. I'm going to draw them in as green circles to indicate they're neutral. So you've got a neutral green argon atom. It's going to be hit by some ionizing radiation. In this example, we used gamma. That's going to knock off an electron, and now you have two ions. You have a positively charged argon ion, and you also have an electron, which is itself an ion. We're going to look at the Geiger-Müller tube next, but just a little kind of fast forward to make the explanation a little easier. In the Geiger-Müller tube, we're going to have a lot of argon atoms, not just one or two. And they're also going to be in a high voltage electric field. So something interesting happens here. We're going to refer to it as an avalanche of electrons. Please note, I'm not saying chain reaction, okay? It's just like an avalanche of ions. So what happens here is you get some ionizing radiation. It's going to hit one of the argon atoms, just like we explained before. It's going to knock off an electron, leaving you with the two ions. But these ions are now going to move themselves. They've got a lot of energy, and especially in the high voltage electric field inside the Geiger-Müller tube, they're moving at very high speeds. And they're going to knock off other electrons from other argon atoms, which are in turn going to knock off more. So you've got this kind of knock-on effect, which we're going to refer to as the avalanche of ions. We're now in a position to have a look at how the Geiger-Müller tube actually works. So to start with, you're going to get a aluminium kind of tube with one open end. Now the reason we're using an aluminium tube is that'll actually shield the inside of the Geiger-Müller tube from radiation from directions that you don't want it to measure from. So we leave it open-ended because that's where we're going to measure for radiation. But the sides will shield it from alpha and from beta. Fortunately, gamma will penetrate right through that aluminium. It doesn't do anything to stop gamma coming in, but it will stop alpha and beta from coming in from the sides. So you've got that aluminium tube, inside of which you've got a cathode, a kind of cylindrical cathode. So the whole inside of the container almost is the cathode. So it's got a negative charge. Then down the middle, you've got the positive anode, kind of like a rod going right through the middle of the tube. And you've got some insulation on the side. Just a quick note here, we're looking at this obviously from the side. This is a 3D structure, so we're kind of drawing as a rectangle. This is a cylinder you're looking at. So you've got some insulation to prevent the anode and the cathode from discharging directly into each other. And at the very top of the Geiger-Müller tube, we've got this thin layer of a mineral called mica, which will allow radiation to pass through, even alpha. Alpha can even get through mica. Inside the tube, we've got some argon moving around at a low pressure. It's kind of bouncing around the show. And we've also got it connected to a power supply at a very high voltage of 400, 500 volts plus, connecting the anode to the cathode. This creates a really strong electric field between the anode and the cathode inside the tube, so that when we do get some ions, they're going to be attracted directly to the positive and negative electrodes. Okay, it's also connected to a speaker, which can also be combined with a little counter that makes so the speaker will make those clicks that you see in the movies, and the counter will actually give you a number for how many discharges you get. And you might notice here that in the absence of anything else, this is an incomplete circuit. There's nothing joining the anode and the cathode inside the tube. But this is where ionizing radiation, enter ionizing radiation, stage right. So here we've got alpha, beta, gamma. I've chosen beta as an example today. Could have gone with any of them, which is going with beta. So it's going to come flying along, moving at very high speeds, passes straight through the mica. It's going to hit one of those argon atoms, and it's going to knock off an electron, like we discussed, leaving with two ions, a positive and a negative. They're going to be accelerated because of the really strong electric field inside the tube. So they're going to be moving very fast, and they're going to hit other argon atoms, and they're going to ionize them as well. So you're going to get more and more electrons and positive argon nuclei bouncing around the shell. So you've now got a lot of charge carriers in there. The positive charges, the argon atoms, ions, are going to be attracted to the negative electrode, and the negative electrons are going to be attracted to the positive electrode. So they're going to discharge, and that's going to create a current. Now it's a very fast and small current. It's just there for a tiny fraction of a second, but we can measure it. So at the same time that the electrons are discharging at the anode, the positively charged argon ions are attracted to the negative electrode, where they can pick up electrons from the circuit and go back to being neutral again. So each time there is one of those electrical surges caused by the ionized gases, that's registered by the counter. So we can use that to quantify how much radiation is coming off a source. So the Geiger-Müller tube can be used to detect to quantify how much ionizing radiation is being given off. But let's just go back and remind ourselves what that ionizing radiation is and where it comes from. So it comes from when you have an unstable isotope that emits some form of nuclear radiation in order to become more stable. So for the purpose of the next explanation, I'm going to be using these kind of orangey red colour to indicate that something's unstable, and after it gives out some radiation, the green indicates that it's a stable isotope. Okay, so radioactivity. Well, activity is how many of these decays are happening per second. So it doesn't matter if we're talking about alpha, beta, or gamma, but how many of these decay reactions are happening per second. The unit for it is the becquerel, named after this very well-bearded individual. But the only thing is becquerels are quite small, so really we'll be dealing with mega becquerels or kilo becquerels. That'll be the unit we'll be mainly using. So let's imagine we have a certain quantity of an unstable isotope. Now the thing about the radioactive decay is it's quite random. We can't predict exactly which unstable nucleus is going to decay. It could be this one, it could be this one over here, and it could be this one. It's quite random. We can't predict it. But what we can do is we can calculate the rate at which it happens. So we might not be able to tell which individual nuclei is going to decay, but we can tell the rate of that decay. We're going to keep on with this orange for unstable, green for stable convention just for ourselves. And let's say we've got two masses of a radioactive isotope. Let's call the smaller one A and the bigger one B. Now they're both the same unstable isotope, so they're going to decay at the same rate. But it should be obvious enough that because there's a lot more nuclei in B, that there's going to be more decay reactions happening per second than there is in A, simply because there's more nuclei there. So the more nuclei you have, the faster the rate of decay is going to be. So that rate of decay is proportional to the number of undecayed nuclei that you have remaining. Now the constant of proportionality in this case, first off it has its own symbol, lambda. It's called the decay constant, and the bigger that number is, the faster that isotope decays. As for its unit, well, if the rate of decay is lambda times the number of nuclei, that means that lambda is the rate of decay divided by the number of nuclei. But as rate of nuclei is the number of nuclei per second, that's number of nuclei per second divided by number of nuclei gives you per second. So the unit for lambda is per second. So different isotopes will have different decay constants, meaning that they decay at different rates. But that constant will be the same for all of that one isotope. So it differs in between isotopes, but it's the same for one radioactive isotope. So there's another measure of this, which is half-life. Now half-life, there's actually two definitions to it. The first we're going to look at is if you have a mass of a radioactive isotope, an unstable isotope, the half-life is just the time it takes for half of those unstable nuclei to decay. That's it. And you'll find that half-life is constant no matter how much you have. There's always a set amount of time until you have half of what you began with. Another way to define half-life is the time it takes for half of its radioactivity to decrease. So every time that a nuclei decays, it gives out radiation. And at the time it takes for that to half, that's because half of the nuclei have decayed, therefore your radiation is halved as well. So it's the same, two kind of sides of the same coin. Okay, so different isotopes will have radically different half-lives. Some in the millions of years category and some in microseconds. And there's a relationship between the decay constant and the half-life. As you'd expect, if the decay constant, the bigger the decay constant, the faster the rate of decay, then you'd expect that the bigger that number is, the shorter the half-life, because it will take less time for that amount of radioactivity to half, for the nuclei to decay. And you're right. So the relationship is, you don't have to prove this, but I do want you to get comfortable with using your calculators for it. It's the half-life is the natural log of 2 divided by the decay constant. Again, you don't have to prove it, but you have to be comfortable enough with your calculators to do on the day. So that's log to the base e. Okay, quite a tough one there today, I think. To finish with, I'd like you to read through the worked examples and have a look at the textbook questions. I'd strongly recommend looking through those worked examples first. And as always, I'll post up the solutions a little further down the line. I'll give you a chance to get to them first. The good news is we've done most of the kind of cognitive heavy lifting for this topic. We've got one last lesson to kind of tie things together, but it's relatively handy compared to what we've just done. So one more coming your way, and then we'll move on to fusion and fission. Okay, as always, any problems, any hassles, don't hesitate to contact me, and best of luck.